I would like to welcome everyone again at NIR conference. In a couple of minutes, we will continue our keynote lectures. So, in the topic will be related to automated driving and Barys Shyrokau, he will talk us about vehicle motion control for safety and comfort. Barys represent Delft University, Technical University of Delft, Netherlands. He worked in there as a professor for 5 years, if I'm not mistaken. It's a really honor for us to invite him and to listen him and to get recent results from collaboration with the major car manufacturers all over the world. Please, Barys, take your time. So 40 minutes for presentation. You can briefly introduce yourself while people are coming back from the lunch.
Thanks a lot, Alexander.
Barys, you can start.
Okay, thanks a lot. First of all, thanks a lot for Alessandra, for you, and also for organizers of this conference to invited me. My pleasure. My topic today will be automated driving and specifically focus on the vehicle motion control for safety and comfort. And before I go ahead, I would like quickly to explain from which department I'm coming. I'm working in the section of intelligent vehicle, what was established in 2016, and this section is a part of Department of Cognitive Robotics in Delft University of Technology. And in this section, we have three major directions: machine perception, dynamics and control, and human factors. The section is led by Professor Dario Gavrila, and the goals that we would like to improve safety, comfort, and efficiency of the future automated driving transportation. Mainly, we are focused on vehicle-based technologies. Like my colleagues from machine perception, they are working to address challenges related with complex unstructured environments, also how to deal with vulnerable road users. The colleagues from human factors focused more on HMI and driver itself, also as passenger. We'll talk a bit about this later. And in dynamics and control, we are mainly considered critical driving scenarios, and also with the tasks related with control and user accessibility. Overall, the interaction between these three subgroups leads us that we have the whole pipeline starting with involvement or non-involvement driving in the loop, perception, 3D environment perception, prediction of the road users, their behavior, and also communication in the way with the passenger, how to improve comfort of driving. In general, you might consider this that nowadays automated driving for highway automation 99% ready if we're talking about normal driving conditions. Of course, in the case of safety critical scenarios, the situation is more difficult. And from the point of environmental perception, this is the screenshot of the driving in Delft. You see that a lot of pedestrians, cyclists, a bit of chaotic behavior. These make the challenges for our perception group and also their research more important compared with normal highway driving. In general, when we're talking about automated driving, of course, the key things, what is mentioned here, environmental perception, how we are going to provide feedback to the human, how we will inform outside external HMI, vehicle-to-vehicle communication, vehicle-to-infrastructure communication, important aspects. Also in this content, energy efficiency becomes important, environmental friendly. The big topic in general is validation homologation, especially for the higher level of automation. According to the IOTA research, we will need approximately 14.2 billion of kilometers to prove that the vehicle is safe. And this is physically impossible to achieve. That's why we also observe a lot of mixed simulation and real tests. But as I said before, the primary goal on the talk for today is control for safety and comfort. And this leads us to the research agenda for today. First, we would like to talk about safety critical maneuvers caused by different weather conditions, wrong driving style, then comfortable drive. And from this point, that you might have a vehicle which is driven autonomously, but if it leads to the level of comfort which is not expected as you want, you simply as a customer will not accept this. And also important for level 2, level 3 automation is an interaction with the driver. These all challenges, we believe, that can be addressed by control of multi-actuated vehicle with multi-objectives while operation. And the final goal, how we see this, is a 6D plus vehicle motion control, using some novel sensor technologies and using as well multi-objective optimization-based control to achieve these goals. What it means 6D plus and why plus is there. In total, we are talking about full body vehicle motion control. We are not only do the control in the plane, also enroll the body dynamics from the point of vertical motion, roll, pitch. And also we consider some additional feedbacks like haptic feedback or maybe in future active seat. We would like to come up to some framework which will be feasible at the end to implement it and cover all these challenges. Let me start with safety-oriented research, and I would like to first discuss sensor technology. Of course, I would say for example, for the localization and for environmental perception, we nowadays have a good combination like sensor fusion between LiDAR, between camera, between radars. Unfortunately, when we're talking about tire-road interactions, only what we have until now is wheel encoders, and we can use accelerations of the vehicle. What we see now in the limitation of the safety, that often the motion planning is done based on the kinematic models, and these kinematic models doesn't take into account interaction between tire and road, which often result in unfeasible planning paths. When we're talking about existing stability systems, there is no direct transition to the automated mode because it was designed to prevent human, and it means that it's not fully utilize the friction potential what can be achieved. The third thing that when we're talking about path following, very often the simplified vehicle model used, and at the end, this could be the reason to cause motion instability. Of course, the hot topic nowadays is a deep learning, and we believe that in 95%, especially for normal driving conditions, this could be covered. However, for safety critical maneuvers, the wrong prediction could lead to the potential collisions and accidents. As I say that we don't have nowadays the sensor which can give to us tire road forces. And we, together with our bearing manufacturer partner, SKF, developed a concept which is called intelligent bearing, which you can see on the right screen. This is a knuckle and bearing which instrumented by strain gauges, and it's allowed to accurately reconstruct the tire forces up to 10 Hertz, which is in primary range of the vehicle handling and usually in the range of interest. It's commercially feasible from the point that there is a research related with smart tires. They have own advantages and disadvantages, and the main disadvantages from the point of operation time. If you change your tires, you need to recalibrate and do the procedure again. And the main thing that we see that it will be beneficial additional information source for future automated vehicles. I would say we are not only one, in this case, SKF is not only one, the company who try to build such kind of technology already for the last 2 decades. The close by will be Schaeffler from Germany, or it will be NTN from Japan, or Iljin from South Korea. There is attempts to build such kind of sensor. And in the past, SKF tried to use approach to measure the forces and directly map to the strains what you measured in your strain gauges. The thing is that, of course, instrumented of the bearing of strain gauges, just glue them. It's not a rocket science. Everybody can do this. And then in the past, for example, our industrial partner use neural networks trying to catch direct tire forces and find the magic black box relationship. It was partially successful, but it was also raised the question that in the case if you produce any new bearing, you need to do the same procedure. In the case of something change, you need to do this on the field. You cannot do it in the lab, which is increased final costs significantly. When we start work on this project, as a scientist, the first decision was that we don't want to find a magic relationship. We need and want to consider the modeling of the bearing inside the estimate. And the approach what was taken was a cascade Kalman filtering approach. When we have extended Kalman filter to translate local strains to the rolling elements loads, and to define inboard and outboard rolling element loads. Then use unstand Kalman filter for the bearing model to translate it to the bearing states. Based on the bearing state, we can calculate the loads, calculate deformation, and then send information regarding the raceway deformation and contact angles to the filters again. Here you see an example when we do one of the field tests, which is called skid pad. Mainly the reason of this test that we try to push vehicle to the limits. And you see the lateral force. The gray one is our ground through velos. It's a wheel force transducer. And the orange one is intelligent bearings. What you see on this photo, this is a wheel force transducer. The reasonable question will be that, okay, why we need to develop the sensor if we already have such kind of technology, we have a ground truth. The problem is that price of such kind of one wheel is approximately 100, started, I would say, from 100,000 for one wheel. It means that to have a full vehicle instrumented plus vehicle costs, I don't think that it's a smart idea to pay $500,000 only for this. And we were also limited and considered that we need to develop the system, which in general, the total cost should be below 1,000 euro. And when we perform experiments and analyze experiments, we also compare with some reference study, which is a pure data-driven approach. In this case, let's say neural networks. And what you see on these plots, the main forces related with longitudinal motion and normal force, and as well the moments, which is commonly used in the control. For example, from this moment mx, you can recalculate lateral force. What we see that the approach what was developed provide a good quasi-static load estimation. Also good estimations, reasonably good estimation in the case of fast transient maneuvers. There is, of course, some things for further improvement related with underestimation of vertical forces, for example. However, in the same time, when we compare with reference study, we clearly saw that the poor data-driven approach show considerable errors compared with the proposed one. But after this, the project was back to our industrial partner for the product development, and we of course wanted not only to develop the sensor and estimator behind this, but also to see how its influence on the vehicle motion control. And the step what was taken for this in collaboration with Toyota, based on the classical example, wheel slip control, anti-lock brake system, how we can develop more proactive controller using, in this case, nonlinear MPC, and also assuming that this wheel load information is available. In this case, what we did, we take estimation errors what we have from our sensor, also with sensor noise incorporated in the simulation environment, and we compare with industrial rule-based controller from one of the tier 1 supplier for the Toyota. What we saw that clearly for the first ABS cycle, which is the most challenging, I would say, we had approximately 75% of improvement. And also in the case of the friction transition, the recovery was much higher. Briefly explaining the approach, what was behind this, that we use a 9 degree of freedom vehicle model incorporated in MPC framework, activation logic, because you would like to have a transition between system and take into account also driver input. Adaptation scheme mainly due to the fact that ABS problem of wheel slip control is depends on significantly, performance depends on the wheel dynamics, and on low speed you need to modify it. Reference generator, in this case you see that we have something like a mixed classical slip control with some additional force information to make this problem less computationally complex, and it was validated with high-end vehicle simulator model in Toyota. And when we compare the results here, there are two examples presented as a spider plots. One is for wet asphalt, another one for friction transitions. The idea I will take, this is like a main KPIs, but commonly used to assess the performance of such kind of systems. The brake distance will be the most intuitive, and 100% means the best, and then it's going to reduction. And here what you see from the point that rule-based logic from tier 1 supplier perform much less, especially for some of KPIs, and also in the friction conditions, which is also one of the quite challenging scenario for rule-based logic. The performance is much less compared with proposed approach. Then taking the step further, we started to think about lateral motion and also how we can benefit for automated driving in evasive cases. And for this, what we did, the controller was developed taking into account two actions, so that you can steer and brake. Usually, if you have an obstacle, you try to brake, but up to a certain point at the high speed, there is no any more opportunity to avoid collision, and you need to steer. The controller was taking into account the limits of the tire and also the vehicle, considered some requirements regarding the force distribution, also took into account actuator dynamics, not assuming but checking that it's real-time feasible, And also the robustness was intensively investigated due to the variation of external disturbances and parameter uncertainties. What we compared, the last one, what was proposed, which is include like a four-wheel vehicle model, including 15 states and non-linear tire behavior, and it was compared with something which is more common in the literature, non-linear bicycle model with non-linear tire, and also with one of the example which we know will be performed bad, but often used also in the literature, linear bicycle model with linear tire. And as I said that, again, here the simulation results, but these simulation results were performed in soft real time and take into account that the controller should not overrun. What we clearly saw that integrated, in this case, proposed controller, as expected, significantly outperform linear MPC. Here you see lateral displacement and in time domain and also yaw rate. And we clearly see that the rate one, the simple one, has significant overshoot. And in the case of compare with nonlinear MPC, the benefit is less. We don't have overshooting, which is a good thing. However, we have a delays. And with both actions, steering and braking, we can achieve more precise tracking. Now I would like to shift to the comfort-oriented research. And first, I would like to quickly discuss current limitation or some potential extensions what we might have if we are talking about comfort of automated drivings. Of course, for many years, we already have a constrained accelerations in our ADAS systems. In any vehicle what you're driving now, or in modern vehicle, you have constraints regarding the acceleration, what you need to, what system will achieve, and then it will shut down. If we are talking about cooperative cruise control. Now the more trends that implement also adaptive jerk constraints. For example, we have a scenario of lane change, and then in this study, at least, it was investigation what will be the preferable driving style for automated vehicle based on the certain amount of participants, and it's more heuristic approach. And the last thing, what I already mentioned in the beginning, that these two things, path control and vehicle body control, they're isolated and they're not coupled. I mean, they control it by two controllers, and usually in industry rule-based logic apply to synchronize them, but they are not presented in one framework, which leads to some, let's say, suboptimal performance. I would like to keep your attention now on the vehicle which is driving. And first, what you can recognize that usually when you drive your vehicle, turn it out of the corner, the body incline. And in this case, you see that it's clearly diving in the corner. This possible to achieve thanks to active suspension. And in this worked for comfort-oriented motion control. We collaborate with one of the leading suspension manufacturer, Tenneco. And the goal is that we would like to reduce first acceleration discomfort. It means that discomfort which caused by high level of acceleration, what you perceived as a human being. And we would like to focus also on the motion sickness, which is a significant problem for automated vehicles in future. The idea, as you already recognize, something what you're riding your bicycle or driving your motorcycle. You try to incline in the corner to reduce amount of acceleration what you perceive due to the G-force. And for this, you need to do some coordinated control. How we realize this? On the current development, we have some preview-based reference generator, which is nowadays we have such kind of systems, curvature preview in the vehicle for automation. And based on this, it generates some reference roll angle. Then the first solution was to put everything in nice non-MPC framework, but the model is so complex that it simply ran out of real time. And since we are working with industrial partners, hard real time is like a really strict requirement for us for any activities, because the final goal that it need to be tested on the real vehicle. The solution what we come up, we solve optimization problem explicitly using explicit MPC. And we use this explicit MPC as initial guess, smart guess for nonlinear MPC. In this combination, it's helped us to achieve hard real-time performance. Then the further step, due to the COVID, it unfortunately didn't happen this year, but will happen in the beginning of next year, testing on the real vehicle. And the next step, what we are taking, is also incorporating this in the motion planner and combine it with the path following control. For now, how it was evaluated, you see that the whole controller is running on 20 Hz in the rapid prototyping platform Micro Autobox. It's communicated with full vehicle model, validated vehicle model with actuator dynamics, which is running on another D-Space machine, much more powerful at 1 kHz. Then it communicated to the motion platform, which generate the motion of the mockup. If you now look this driving simulator results, but it's driving simulator results when artificial driver, like you are as a passenger in automated mode. What we clearly see that we are looking now on PSD lateral acceleration for 3 different scenarios: highway, rural, and urban. And we are looking on the frequency range, which is corresponds to the motion sickness. We clearly see that we can significantly improve, compare the proposed one, the last one, and MPC. Explicit one will be the solution only based on the offline optimization. We also take into account one of the options when we have a PID controller, just a classical one. Passive case, as I say, that there is no any action applied. We can significantly reduce PSD of lateral acceleration in the target range of the frequency we're interested in. When we later look on the time domain results for the whole track, we observe that on the level of RMS, we can improve compared with the passive case, of course, up to 52% for highway scenarios and up to 32% for urban driving. As I said, the next step also will be to do this on the full real vehicle with the human participants. And now we are coming to the point when I would like to tackle a user acceptance, and we already have some discussions regarding in the previous lectures regarding the haptic control, and we are also strongly believe that at least for the next several decades, we still be not fully have all SAE level 5 automated vehicles. I would say we are now here and we see more introduction of also SAE 4 vehicles, which is perfectly run on the proving grounds. However, taking into account the fleet, some predictions for 2045, we will have only 20% of automated vehicles fleet in Europe. Which means that another 80% will be in some still on the level 2, level 3 transitions. And we would like to improve the current ADAS systems when the human still can act to can act and take control or work together with, ideally work together with IE. And in this case, we are talking about collaborative driving, and this work is done in cooperation with University of Cambridge, with Professor David Cole and his team, and also with our industrial partner, Toyota. The idea is that we have a driver, we have some ADAS systems, we have a closed loop man-machine interface, and they're both um, uh, contribute to the vehicle driving. If we're talking about literature, there is a lot of research related with driver models, and what we find very interesting is the work which is performed in Cambridge on their driving model, because it can predict accurately predict steering driving torque, and it's also captured driver intervalability. This was the reason to go to this model and incorporate this part of this model as a cognitive function in their muscle dynamics to MPC framework for the shared haptic steering control. And then we wanted to compare with the state-of-the-art system which is used in Toyota, both subjectively and objectively. How we did this, as I said, the driver model was incorporated in the MPC framework. This was not enough, but we wanted to extend this, and we come up with some adaptation optimization algorithm to change weighting in MPC to consider better adaptation to the driver style. And both controller and participants control the vehicle, feedback provided by control loading, and it's going to the driving simulator. In this case, the simulator was fixed based, but also the maneuvers, what was considered is more like a normal highway driving, when you don't expect a lot of contribution from the motion platform. Motion platform is not needed in this case. And I would like first to discuss subjective results. You see that we perform questionnaire regarding the overall steering effort, past tracking performance, how was collaborative system or not, how smooth was control, and feelings to be in the control, which is very important for the human being. The green one is ideal range. The baseline in this case is state-of-the-art commercial system, which is currently in Toyota vehicles, is a blue one. Standard means that this is MPC incorporated in the driving model. And the last one, what was proposed and what was implemented with additional adaptation to better reflect on the personalization and driving style. And as you might recognize, for all of the subjective questions what we were addressed, we outperform baseline for sure, and in general we're in the target range. When we later look on the objective key performance indicators, we presented on here, I will show only two of them. First is lateral error, deviation, and the second one is a collaboration ratio. If you're interested in more of the KPIs, the paper will come in soon, approximately in 2 months it will be published. It's in the final round of review. And we clearly see that reduction of the lateral error significant. Compare with MPCs and baseline, we can reduce up to 36%, and we also can significantly increase up to 63% collaboration ratio. This was done on the pool of 19 drivers, which is quite representative. And now the step further, what is taken, that there is adaptation and implementation for the real vehicle, and we hope to perform the same experiments to show on the real car as well. Then some outcomes from what we discussed. For safety critical maneuvers, we are targeting to achieve better safety thanks to proactive actions, coordinated control, and new sensor technology. To achieve comfortable ride, we wanted to reduce the perceived acceleration and specifically target to the motion sickness. For user acceptance, yeah, we believe that it's needed for the high level automation, and the collaboration need to be increased. And for overall framework is flexible to implement additional functions regarding the energy efficiency and also for additional degrees of freedom. I also would like to take a chance and to explain a bit our in-house activities. This driving simulator was developed in our group, and it consists of Steward platform and mock-up and visualization system. We perform 4 different directions of investigation on it, related with critical safety-oriented scenarios, comfort, biomechanical studies, and as well human-machine interaction. And the thing is also now we are starting to look more in the motion cueing, how to improve this. And quickly overview of the ongoing research projects. For comfort-oriented motion control, we're mainly working in this project with our industrial partner, and we would like to come up with better comfort for automated driving. We started several projects recently for next step regarding the load sensing technology, this new technology developed with bearing manufacturer. We now move into the phase that we have a project when we will try to incorporate this technology as well in evasive maneuver for automated vehicle, and see in next 4 years what kind of real benefits we can achieve. Thanks that we have on board Volvo Cars and Toyota to support us, also Siemens. And we have internal industrial project with Toyota regarding the motion sickness and specifically simulator sickness, to look for how we can extend and how we can in motion planning solve potentially problems related with motion sickness. And the last is more focused on electric vehicles, but in the same time, it's give to us some sport where we can investigate how the driving simulator, what we currently have, up to what kind of level can be used to investigate the things related with comfort and specifically with motion sickness as well. If you would like to know a bit more specifically regarding my colleagues, I would recommend you to visit our website or follow our YouTube channel. Specifically regarding the environmental perception, there is a lot of videos and just some recent best paper awards and talks from IV 2020. Thank you very much. I open for your questions.
Thank you, Barys, a lot for your very interesting presentation. So we have a question in the chat, so I will read it for you. On the you talk about the safety problem, okay, but there is another issue related to cybersecurity of electronic system. A few years ago, some kits of electronic devices of modern vehicles were successfully cracked by Miller, Velasquez, and others.
Yeah, I also read it. Yeah. If you wanted to complete,
so can you comment on this? How we can work, which sensors we can use?
Yeah, I would say that of maybe a bit of confusion when we're talking about safety, and we can also talk about active safety. And I think that the work what I presented, it's more in the domain of active vehicle safety. It will be more proper term. We also have a passive safety, which is when you crash a vehicle. Cybersecurity is safety. It also belongs to safety, but it's another type, I would say. Yeah, it's extremely important topic, and it's also nowadays not only it's also in the content of vehicle-to-vehicle communication, vehicle-to-infrastructure communication. It's a hot topic, and I am aware, but cannot comment more from the point that it's not my domain.
Okay, so
and we have here another one: how to validate MPC performance in perspective of fully autonomous vehicles. Not fully sure that I understand the question. I mean, if we're talking about full automation or level 5,
probably I can comment. Because MPC, it's somehow it's not a strict approach. So you have some statistical approach inside. And would you be able to validate this technique in future?
I would say that what we're currently doing, we perform simulations, extensive simulation to check robustness of MPC, of varying the introducing external disturbances, and parameters, uncertainties. This is more like a prerequisite from the company, and it's in general, if you have a rule-based logic, that doesn't matter you have MPC or rule-based, the procedure is more or less the same, what kind of amount of scenarios you need to perform. The question is, of course, that in the case of MPC, you will need additional adjustment, weight adjustment, according to some specific scenarios, and this complicate the whole picture. And MPC performance regarding the lateral and longitudinal control, I think the question probably, if we incorporate in one, if I understand correctly, or MPC performance, I would say in general, if you compare the, if you depends with what you compare, but in general, MPC is better. The problem in MPC is if your model is deviate what you have in the control significantly from the plant dynamics, then you're in troubles. In general, what we are trying to investigate now, we are going to the direction learning MPC, that we would like to learn MPC model inside. In compare with PID, outperform. In compare with LQR, yeah, it's your static solution. You have a linear system. I mean, you can use for LPV, but still again, in your formulation, for example, for lateral control, corner and stiffness will be constant, and you simply don't have opportunity to modify it if you're talking about LQR. Then as soon as you go into non-linear regime of motion, the difference will be much more significant. Again, in a nutshell, say that if you're talking about normal driving conditions and specifically path following, I would say there is no big difference between LQR, linear MPC, non-linear MPC. And this coming due to the fact that corner and stiffness of the tire linear. As soon as you push in vehicle to the limits, it's exactly the case of evasive maneuvers, then the situation changed dramatically. And about social aspects, how to give a feeling of being in control for the most of the people that are not familiar with AVs. It's a very good question, and I think it's a question to my colleagues who working also on human factors. And what we are doing, for example, what in the presented study, what we are doing, we ask a questionnaire regarding the just a direct question. do you feel in the feeling in the control or not? I would say that one of the social aspects to be in control is not really what in human factors nowadays in IV asked, but the question is it needs to be pleasure to be driven. This is the main things. You probably, if you're sitting on the back of your car and reading the book, you don't want to be in charge of the control, but you want to be gently driven through the daily road. I hope it's answered your question. Thanks a lot, Kirill.
Thank you again, Boris. And one more question from my side. When we can read newspapers going from home to our jobs, what is the expectation?
Yeah, I mean, for this, we need to solve the problem of motion sickness. And this is the thing that it's a bit strange, but one of the goals of the companies who are working on the suspension is to achieve a train dynamics, train ride comfort, that you can read newspapers in the train, but unfortunately, many of us struggle to do this in the car. And this corresponds to motion sickness. To answer this question, I think more investigations need to be done. In some way, automated driving is a hype, and but it's also create more questions.
Okay.
Yeah.
Thank you again. It was a
Welcome.
pleasure to hear you hear your lecture. So thank you again.